So I'm delighted to start the afternoon session today with an exciting talk, review talk on transformers of bootstrapped amplitudes by Francois Charton. Please, Francois, the stage is yours.
Okay, so yeah, you can hear me. I'm Francois Charton. I work in Meta. I'm not a physicist, I'm a computer scientist, so I'll redirect all the technical questions to Lance Dixon, who's here and who's on those papers. And I'm mostly interested in using AI, using language models, so small language model, not ChatGPT, that kind of things, to do mathematics and physics. And more precisely, I'm interested in considering mathematics as a translation task. Said otherly, I want to train models, language models, to translate problems of mathematics, of physics, encoded as sentences in some language into their solutions. To give you a short idea, I would like my machine to learn to take the sentence 7 plus 9, 3 words, and translate it into 16, 1 word, 2 words, depending on whether you want a digit to be a word or 16 to be a word, or to have the 6-word sentence x squared minus x minus 1, and to learn to translate it into the roots of the corresponding polynomial or anything else. So to give you a more precise example, it's a paper I did recently. If you train a model to learn the GCD, the greatest common divisor of 2 integers, so suppose you have 2 integers, 10 and 32, the GCD is 2. I can encode 10, 32, and 2 as sequences of digits in base 10, encode them as we write them. So it's plus 1, 0, plus 3, 2, plus 2. By the way, I call them plus 1, 0 for your benefit. In practice, it could be red, blue, yellow. It could be any word. The machine doesn't care about the meaning. It's all symbols to them. And I want the model to translate plus 1, 0, plus 3, 2 into plus 2. And the idea is that the model should learn that just from examples and as a pure language task. There's no mathematics built into the model. So the recipe for this kind of thing is that you want to learn from examples. So you need to generate or to take, in the case of physics, a lot of examples of problems and solutions. You're going to encode them as sentences in some language. And you're going to train a transformer model, which is the basis of language models, from problems and solution by minimizing, we call it the cross entropy. It's the correctness of the solution, basically sort of a Hamming distance between the predicted value and the correct value. And at this point, there's absolutely no math. And then once the model is trained, you're going to test it on a held-out test set, so solutions that the model hasn't seen at training, and use a mathematical criterion to see if the model learns math. And the funny thing is that this works. I've been doing that for about 5 years. We've been using it to do symbolic integration, so compute the symbolic integrals of functions. We do that better than Mathematica, so yeah. We've been using it for dynamical system, most recently computing Lyapunov function, which is an open problem. We use it for symbolic regression. I'll show you that. I've been using it with others for cryptanalysis of PQC, post-quantum cryptography. And there's one application in theoretical physics that I'm going to present. So first, I'd like to interest you in it by a paper of 2 years ago. I'll go quickly on this with Stéphane Dascoli, Pierre-Alexandre Camiani, and Guillaume Lample, where we wanted to, so basically the problem we tried to solve is IQ test. You have a sequence of integers, and you see the sequence, and I say, what's the next integer? And you're supposed to find that. So when you think of it, there are 2 ways to do that. There's a numeric regression approach, the time series approach. You look the numbers very hard in the eyes and you predict the next one. So you want a function from the input to the output. But that's not what we humans do. We typically do symbolic regression. When we do that, we look for a formula that accounts for the sequence. It could be a closed formula, or more probably, if you did it right now, it's probably you found the recurrence relation. And you use this recurrence relation to find the solution. So the idea was, could we train a model to do exactly that, to predict the next number? So we have 2 tasks, numeric regression, symbolic regression. We want to compare how the models learn. We have 2 settings, the integer sequence, which is the IQ test, and the real floating points, floating point sequences, which correspond to a more scientific or more practical problem. But there's only one evaluation criterion. We want to see whether the model, no matter whether it learned to predict the next term or a function, is good at predicting the next elements in the sequence. So in order to do that, you need to generate data. So just to give you an idea of what needs to be done to do that. So you generate a random function, n plus un minus 1. You're going to need to sample the initial point if it's a recurrence, or the one, so I need only one point here. And you use this, the function, to compute all the terms in the sequence, well, many terms in the sequence. And then if you do symbolic regression, you feed the model with the first terms in the sequence, 1, 2, 4, 7, 11. And you expect the model to learn to predict n plus un minus 1. And if you do numeric regression, you have the same input, but the output are the next terms in the sequence. How do you encode the data? Well, the numbers, you can imagine, they're just sequences of digits, so you need a separator to separate them. It's very easy to encode. How do you encode functions? So it's something we've been doing all the time. It's very easy to represent a function, any function, as a tree. You know, a tree where the internal nodes are the operators of the function, and the leaves are either the variables or the coefficients, whatever you have. And so you can see on the left, 2 plus 3 times 5 plus 2 is this very simple tree. And if I get a little more creative and add variables and powers and cosine, I can get a more complicated function. And I can push this further by having, you know, differential operators, whatever. And the good thing is that once you have a tree, it's very easy to enumerate a tree. You know, you just read in some order, Polish notation, something like that, and you have sequences. So that's a good way to represent any mathematical object as a tree and then a sequence. And when you generate, it's also practical, because when you want to generate a random function, you know, what's generating a random function? If you know that a function is a tree, then you generate a random tree and you put random operators inside a list. And that's what we do here. So you have a list of operators for integers and a list of operators for floats. There are more operators for floats because the operators need to be closed, you know, in the space you're working on. So you have less of them available for integers. Anyway, the main results were that. So you see the top table. So there are two models, the symbolic model that predicts a function and the numeric model that directly predicts the next values. I have the integer and float sequence case, and I have two subcolumns which correspond to small functions or large function. N ops is a number of operators in my function. So, and you can see that the funny thing, and this was unexpected to us, was the symbolic model always works better when predicting recurrences and that kind of data. And so the model does exactly like we humans do, even though, you know, intellectually, it seems like a more difficult task to have to predict a function and get down to the values, but it works better. If you have longer, so the rest is scaling things, it's more difficult to do floats than integers just because you have more operators, so the problem space is much larger. And it's more difficult if the functions get more complicated. I'm passing on the scaling laws below, they're not really useful. Here are examples of successes on the left and failure on the right. So you can see that the model is good at, so the green part on the left is the data the model had, and the blue part or light blue part on the right is the part the model predicted. And you can see that for the success, the model sometimes managed very complicated function, very easy function. There's no rule. For failure, it's even more interesting. You have fairly easy things. This one, for instance, that the model fails by a very, very small margin. You have things where it's sort of managed and then fails, and you have this one where it's totally wrong. So there's no real pattern on how the model learns, but the model still managed to do relatively complicated things with that. So, of course, here, everything I'm testing, I call that in-domain. I'm testing on examples of functions that I generated, that I know are recurrences, that come from the same distribution as the data I used to train my model. So I'm sort of cheating. So the real test set is, okay, how does it do on sequences that are maybe not even recurrences? And in this case, we are lucky because we have OEIS, you know, the online encyclopedia of integer sequence, which is a huge data set of all kinds of sequences, not all of them mathematical, but you have the number of stops in the Brooklyn subway lines in OEIS, for instance. You have the prime, so not recurrences, you have lots of things. So you can see here what happens if the symbolic model for those OEIS sequence. So the performance drops. That's normal. The model is trained on recurrences and you test it on things which are not recurrences. You've got to expect some kind of failure, but still 33% correct prediction is not bad, at least for us. The numeric model works better than the symbolic model in this case because I believe because looking for a recurrence doesn't help for some of those sequences. But most interestingly, the two last lines correspond to Mathematica performance. So we are far better than what you would call the state of the art on this task. Okay, so these are examples of the funny things that the model can learn. These are all OEIS sequences. And I'd like to end up by showing you two things, and then we will talk about physics, promise. So the model here, so far, you know, the model is okay, we train the model to do something and it sort of does the task, but do we learn math? Are we learning something? And here is an interesting example. So the model, as the functions I'm creating in the models, have all kinds of operators, but the coefficients are only integers. This was a limit in our generation method. So the model doesn't know how to write a function which has non-integer coefficient in it. In other words, it cannot write the word 0.3333, doesn't exist. It has to approximate it with a function using integers. And so we try to use this model to approximate real constants by expression only featuring integers. So you can see if you give the model 0.3333, it's going to say, oh, it's 1/3. Good. If you say 0.3, you cut 1 free, it's going to give you this expression, which is, okay, it's a little less than 1/3, right? It's 1/3 plus a small number. The next one is even better because it has pi as a constant. Pi was defined as a constant, so it's in vocabulary. If you give pi to enough digits, the number will recognize pi. But look at the one at the top. This one is absolutely great. It looks like crazy until you remember that, you know, arctangent infinity is pi divided by 2, right? So twice the arctangent of a very large number like exponential 10 will be a little less than pi. And so on. On the right, it's the same thing. So instead of asking for constants, you know, for numbers, we said, okay, can you approximate function? So the model is limited to its vocabulary. And in the vocabulary, in what the model had been trained on, there were no hyperbolic trig functions, for instance, and no Catalan, Dawson, Bessel. But the model, if you give it the values, it will manage to find the correct formulas for the inverse hyperbolic trigonometry. And it will get you a good approximation of the Bessel function, even though it's absolutely not in its vocabulary. So I'm showing you that to show that I'm training on a task that has nothing to do with higher mathematics, but the model is still apparently learning some things mathematical. Okay, last thing that's for the fun. So when the model trains, I told you it doesn't know numbers. The numbers are just symbols. I could rename all the symbols. But over time, as you show examples, the model learns how to embed the symbols in a very high dimensional space. So this is the projection, it's a PCA, of the numbers of the integers and the floating point exponents once the model has been trained. And so the model starts from scratch and it learned a good representation for the numbers. And you can see that all the small numbers are, can I make this work? Yes. This is the number 0 to 10. And then, you know, it grows as you move downwards. You can see the squares here, 25, 49, 61, 81, 121. I don't know what it means, but the model obviously is learning something here. Same on the exponent. You can see the nice symmetry between the positive and negative exponent, which correspond exactly to the mapping from x to 1 on x, which is a function that appears all the time, you know, in the calculation the model had to learn. So I'm stating here that, you know, these models are more than, you know, educated dogs or nice automatas that can do some tasks. They really seem to learn something. Okay, now onward to physics. So we're going to talk about scattering amplitudes and bootstraps. So, okay, I'm going to read those, but this is meant for a computer science audience. So scattering amplitudes, complex function predicting the outcome of particle interaction. They're computed by summing Feynman diagrams, and they're computed to a number of loops. and which correspond to virtual particle. It's a hard problem because every time you have a loop, you have two latent variables, and the integration gives rise to generalized polylogarithms. So that's what we saw this morning. You know, if you want to do that in the standard model, you can reach loop free, etc. But that's pretty much all you can do. So Lance and his colleague have been working on amplitude bootstrap, which basically leverage the properties of polylogarithm so as to predict the structure of the solution to the coefficients and then compute integer coefficients from symmetry consideration, knowing limit values, symmetries, etc. So it happens that in planar n equals 4 supersymmetric Yang-Mills, the solutions are relatively simple. That is, you can compute the amplitudes from symbols, which happen to be homogeneous polynomial of degree 2L if L is the loop, with integer coefficients. And specifically, they've been working on something called the free gluon form factor, which is in n equals 4 SUSY, free gluons and a Higgs. And in that case, they could compute the symbols for the amplitude up to loop 8, which is quite a lot. So in this specific problem, the amplitudes for loop 8 can be computed from symbol as homogeneous polynomials in 6 non-commutative variables, A, B, C, D, E, F, with integer coefficients. So you can see the beginning of loop 3. You have -4 B, C, C, A, F, F, 6 letters, +4 B, C, B, A, F, F, etc., etc., etc. There are 6 to the 2L possible keys, possible sequence of 6 letters, which are mapped to integer, but most of them are 0. You can see the number of non-zero terms on the right. So for loop 3, you only have 600 non-zero coefficients. Okay? And this is usually, or this has been calculated by using symmetries, asymptotic properties, which become constraints. So it becomes a gigantic integer programming problem that allowed, well, Lance and his team to calculate up to loop 8. Now, there's another way to look at it, and I call it the 6-letter game. Basically, what happens is that we have keys, which are sequences of the 6 letters, 2L letters, and integer coefficients. And there are relations between those keys and the coefficients. There are obvious relations, obvious symmetries. So it's known that the coefficients are invariant by the dihedral symmetry generated by, ABC, ABCA, DEF, D, and the swap of AB and DE. So BCAFF maps to -C, but so does ABBCEE by symmetry. Every time you have one coefficient, you have actually 6 of the same. The non-zero coefficients are also constrained. All the keys must begin with A, B, and C, and end with D, E, and F, and there must be no contiguous A and D, D and E and F, etc. So there's a number of rules that can be derived, I think, from theory that constrain all those symbols. There are also a lot of less obvious symmetries. So for instance, if you look at non-zero key that end with just one letter, D, E, or F, they must be preceded by a run of just one of the letter A, B, or C. So you can have a key ending with E, C, 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 D, which could be non-zero. But if it was E, C, B, C, D, it must be 0, no matter the loop, no matter the... This is the way. So I don't think there's a theoretical reason for that, but it's been observed on all keys that we have until loop 8. And there are other empirical facts which seem to hold true. Large absolute coefficients happen for symbol with very few letters and long runs. So there seems to be a lot of information inside the symbols. And since my transformers are pretty good at, finding weak signal, could we use one to pick up these signals and hopefully either calculate the loops or learn interesting facts about them? So the first experiment we did was, okay, can we predict the zeros? Most of the coefficients are 0, a few are non-zeros. So I'm going for loop 5 and loop 6, and I want to predict whether a term is a 0 or a non-zero. So for this, I'm going to build a 50-50 sample of zeros and non-zeros. So why 50-50? Because if you have 99% 0, the model will learn to predict everything as 0 and never learn the ones. The model works, on statistical basis. So 50-50 of zeros and non-zero. You keep a couple of terms for the tests that the model will not see at training, and you see if the model is capable of predicting from a sequence of letters the value 0 and 1. And it works. You can see that on loop 5, after training on just 300,000 examples, that's about 57% of the non-zero keys and as many zero keys, the model predicts 99.96% of text examples, so all 10,000 text examples except 4. So it works. For loop 6, you need more example, but way less of a symbol. So the model has absolutely no difficulty just looking at the letters, saying it's a 0, it's a 1. For us, it's not that easy, but it's perhaps doable. So the next step was, okay, can we predict the non-zeros? So now we eliminate all the zeros, we keep the non-zeros. I give you a sequence of 2L letters, and the model is supposed to predict the values, the corresponding coefficient. And you get those curves. So those are learning curves. On the bottom, you have the time, the training time, measured in epochs, number of examples seen thing. And the top is the accuracy. So there's the percentage in a test set that wasn't seen at training that is correctly predicted. And you can see that the model learns. It eventually reaches something which is very close to 100%, 98% or so. So yes, it can predict the coefficients from the key. And this is quite spectacular because it's doable for human, but you need a lot of theory and PhD students and postdocs to do the calculations. So here, you can see that all the models manage, but there's something funny for loop 6 is that you got 2 steps. You see the model goes up and then it saturates at around 50% and it stops and then it learns. And I have many curves because they correspond to different experiments, different initialization of the model, slightly different architectures, etc. So this 2-step curve was a bit puzzling, so we tried to study it. And actually we understood what happened by looking at what the model was predicting. This is the final curve. This is when the model predicts the magnitude, so the absolute value of the coefficient, and this is what happened with the sign. And this was shocking, I mean, because there are only so many magnitudes and only 2 signs. The signs should be easier to learn than the magnitude, but it's not the case, obviously. Even more interestingly, you can see that the magnitudes are learned all at once, and the model must finish learning the magnitudes before all the signs get learned, a bit like a phase transition. So it's something I've been observing since in other problems of mathematics. We don't know exactly what happens here, but it's probably something relatively interesting to learn. So we did more experiments with less symmetries. I told you there's a lot of symmetries in the data. There's a dihedral symmetries, there's the zeros, etc. So the physicists in the group came up with representation that use less symmetries. So they call it quads or octuples, which are the last letters in all sequence are sort of constrained. You only have 8 possible endings of 4 letters, and you only have 93 endings of 8-letter octuples. So if you remove the cyclic symmetry, if you remove the dihedral symmetry and keep the quads and the octuples, you get a compact representation of the data at loop 7, loop 8, with way less information because all the obvious and easy stuff to learn has been eliminated from the data. And you can see with the quads, it works exactly the same. So instead of having 93 million examples, the model only has 7.3 million quads, so very few of them. But it's enough. The model will still learn. You can see the 2-step loop. So the model is not just learning the easy stuff and failing randomly on the hard one. It apparently learns everything. And the same goes with the octuples, even though you can see here that the phase transition between the learning the magnitude on the sign gets a bit strange. There seems to be some kind of coupling appearing here. I don't understand why. So the main takeaways at this point is that we can use transformer to compute partially calculated loops. We could very, very well calculate half or maybe a third of a loop and let the machine finish. We have techniques to verify that the model predictions are right. This is important. The coefficients are learned with very high accuracy. Okay, even when you have a little bit of the symbol, you can learn the coefficients. And you learn a few unintuitive things about the model, notably the thing on the sign, learning the magnitude before the sign, which might correspond to some, up till now unknown properties of the symbols or properties of amplitudes there. So I have, another set of experiments. So here I was only working on one loop. So I'm looking at one loop and I'm trying to complete it. Obviously, the ultimate goal of that would be to predict the next loop, to go from 6 to 7 to 8 to 9. And you can see that it's not an easy thing because obviously, it's the same problem, but these are different Feynman diagrams you're integrating on, etc. There's not a natural relation between one loop and the next. So we said, could we show if a model could do that? So the idea is that suppose you take an element at loop L, it's a sequence of 2 L letters. Now, you would like to find a recurrence relation that links this coefficient to some parent coefficient at the previous loop. And a very simple way of going to loop L minus 1 is to notice that loop L minus 1 has 2 less letters. So you can if you strike out 2 less letters, you get a parent. And you got 2L times 2L minus 1 divided on 2 ways of doing that, right? So that's what we do here. We call it the strikeout. So we eliminate 2 letters, and we have a sequence of coefficients, okay? And we try to find a recurrence relation that would predict the coefficient E of loop L from the parents of loop L minus 1. So you can think of it as kind of a gigantic, because multidimensional and non-commutative, Pascal triangle. In the Pascal triangle, you can compute a value from the parents. It's the same, but much larger and much more complicated. So we try to do that by predicting loop 6 from loop 5. So you have 66 parents, loop 5 coefficient, and you predict one integer, the loop 6 coefficient. And again, you get 98% accuracy, so the model can learn that. So there seems to be a recurrence relation that we don't know, and this is getting very interesting now. We don't know how to find it, but the function exists, or the transformer would not find it. They are very small transformers. So something is clearly happening. So can we find the function? Unfortunately, opening the box and trying to understand what the transformer does is pretty much a lost cause. There are way too many parameters. It's very difficult. But we run a couple of experiments. We can basically modify the data available to the model. We give it 66 parents. What if we give way less parents? Would it still be good? So see if the model still learns if you give it less input. So in this case, instead of striking all parents or groups of 2 letters, we strike only letters that are close to each other. So we say, I strike out 2 letters that are no more than, say, 2 letters distance, etc. So there are less. And you can see the results here. So if you strike 2 and all parents, you get 98% accuracy. But you can see that you basically get the same result if you strike 2 at only 2 of distance. And there you have about, I think, 25 parents or 20 parents, something like that. It gets down if you strike only adjacent elements. So you just have 11 parents in that case. See, strike 2 letters that only choose. So what it says is that probably the recurrence function that we're looking for might not need to have 66 parents, but way less than that. This is the lesson. It's a simpler function than what we thought. We had another try where we tried to shuffle the parents. So instead of giving them in order, you randomly shuffle all the time. And you can see if you shuffle the parents, you get 95% accuracy. So you lose, but not that much. So this goes to show that the recurrence function that we're looking for is probably to some extent permutation invariant in its variable. Like addition is commutative or something like that. So it's to a large extent, not completely, but to a large extent. So we can see by doing those experiments, we can get information about what the model is doing, learning, and the kind of function we're looking for. So that's pretty much what we've done so far. So it was a paper. I didn't put the archive reference of the paper, but I'm sure you can Google it. So the next step, what do we want to do now? Well, it would be great to see if we can build loop 9, because no one has tried. So that would be fun. It's a big loop, though. It would be interesting to go for loops for related problems. And also it's interesting to see if we can discover local properties or symmetries in the symbols. Because, the symbols were calculated by leveraging the symmetries known in nature. If we discover new regularities in the symbol, does it go the other way? And Lance talked about antipodal symmetries and stuff like that. So there are things to be discovered there, obviously. I'd like to finish and show you a couple of fun facts. So these are two models. You remember you have a dihedral symmetry on the 6 letters. If you have a too small model, you got the right thing. This is the embedding. This is a representation in 3 dimensions of the embedding of the 6 different letters. And what's interesting on the left model, which is the model we actually use, the one on the right is a smaller one, you can see the 2 faces of the dihedral symmetry. So the model is learning somehow the dihedral symmetry relation just by looking at the data. This is similar to what we've seen. Another funny thing, there are many relations between coefficients. You know, those relations are used to calculate the coefficients. So we looked whether the model learned those relations. Those are two very simple relations. And you can see that the model learns the relation, the red curve, before it learns all the coefficients, the 2 coefficients. So there's a stage at the beginning of training where the model is capable of predicting the 2 coefficients with opposite signs, or in this case, with the same value, even though the model is not already perfect in predicting that correct value. Yeah. I won't need all the time. I'm actually almost finished. So that's the main result we have. So where are we now? So we have a proof of concept. I would say, you know, so far we haven't discovered anything. We just leveraged the data that was already calculated in loops 1 to 8. But we show that models can predict coefficient from key and discover recurrences from one loop to the next. So the next idea is, could we go to loop 9? Could we go to other problems, or could we scale up? And this is something we want to try. Another question is, could we reverse engineer the model to try to discover the relation they're learning? So showing 3 direction by decreasing order of, increasing chance of success. Looking at the weights, in my opinion, is totally hopeless. The models are very small, but the weights are, you know, it's lots of calculations, some linear, some non-linear, it's trained, everything is stochastic. It's very hard to predict correctly. Looking at the representation learned by the models is probably a much better idea. So you look at how the model represents the digit. You've seen the nice representation of my integers in the symbolic regression case, or looking at how the model represents the keys. Because intuitively, if the model predicts the same value for 2 keys, it's quite possible that the 2 keys lie in the same place in representation space, a high dimensional space. So just by looking at which keys the model classify in the same place in a representation space, we are going to learn, you know, a couple of the things the model has learned. And finally, we could look at the way the model trains, you know, just like we did for the 2-step in the sign. What the model learns first, learns after, tells us something about what the model is learning overall. The other idea which we're pushing now is that suppose we train a language model on all we know about the symbol, like, you know, you train ChatGPT on everything we know about language, which is all the scrapped internet. Will it learn new emerging properties of a symbol? So those are the questions we wonder on. And I'd like to finish and say more generally, this is a developing area of research. So in symbolic mathematics, we're at the point where we're beginning to use transformer to help solve open problems. You know, up till recently, most of the problems we attacked with that were undergrad problems. Some of them hard, like symbolic integration, but there's nothing, you know, it's not a research problem, not at all. So to give you examples of things I've been working on recently, we've been showing that you can discover the Lyapunov function that control the global stability of dynamical system, you know, the embodied problem and stuff like that. So if you have a dynamical system, if you want to know local stability is obtained by, you know, the eigenvalues of the Jacobian. So that's the spectral mapping theorem. But if you want global properties, you need to find a function, like an entropy function called the Lyapunov function. The theory of Lyapunov function dates from 1892, Lyapunov, but there's no constructive way of building such functions. And it's been an open problem for a century. And we have models that are beginning to, you know, do a little better than the best tools we have right now. So this is moving. And I'm working on discovering kernel elements in the Bureau representation of braid groups, so which are things that are useful, notably related to knot theory and all that. So I'm saying that because I think we're at the point where, you know, the machines work well, or the models work well enough to be able to be applied to interesting problem in theoretical physics. And I think that was my last slide, so thank you very much.
Thank you very much also for keeping the time. It was an exciting talk outside the usual way of tackling problems. We have time for questions.
The traditional transformer architecture that you're saying?
The exact, so I'm using the vanilla, really the garden variety of transformers, so encoder decoder. You have an encoder and a decoder. The encoder is bidirectional and the decoder is autoregressive. So it's not, ChatGPT are decoder only and BERT used to be encoder only. So that's the old model. And they are small model. The largest model I have like 30 million parameters or something like that. We are nowhere near the billion parameters of others. Because, well, I tried, but we don't need them. Usually small models are good enough.
Models to understand mathematics, you have to build in some high-order logic structures within models. So I'm wondering if you consider experimenting with architectures.
So I think if you wanted to train the model on all of mathematics, you would need very large model and multitask training and stuff like that. If you're specializing on just one question and you have a way to train in a supervised way, so you have question and answers, you can deal with much simpler and much smaller architectures, I think. Or at least this is my experience of it.
Hi, thanks for the very nice talk. So this phase transition behavior, is it something that you think it's specific of the physics problem? Or if I try to learn with a classifier, I try to classify numbers, integers with the sign, could I see something similar already?
So there's no general rules of sign that would apply everywhere. As for the step functions in the curves, yes, I've seen it happen in many different problems. I've seen it happen notably when calculating GCD. You can look, I have a paper on that, where you really can see the model learning step by step the divisors of numbers, or GCD divisible by 2, and then 3, and then 4, and then 5, etc. And it works by steps. So this is relatively common. What is less common is the idea that you would learn the magnitude before the sign. This is usually the machine will go for the easier problem before the hard problem. So this is more the surprising part. But the step, I like to call it phase transition because they really look like that. The phase transition thing seems to happen a lot in mathematics and in supervised training. When you don't have supervision like, you know, language, it doesn't work. But when you have supervised training, yes, it seems to happen quite regularly.
Okay, thanks.
Okay, we have time for one more question. Yes.
I was wondering, you're hunting for structure in the representation, the final representation of your model, and you showed us some examples. Your examples look like the representation is 2-dimensional or 3-dimensional, but I'm guessing the real representation is actually... So hunting for this structure, is it an art or is it the science, you would say?
So, so the projection is 2-dimensional, 3-dimensional, because I need to write it on slides. And typically we do, I like to do PCA on that. So when you do a PCA, you know, the principle is that you lose as little information as you can. But I agree that what I've shown you here is not science. It's really illustration more than science. I wouldn't even call it art. If I were to look at the representation, the last thing I would do would be a projection, because I wouldn't want to lose the small signal to that. So you are working in very high dimension. And the intuition we have from language model from other areas is that the model uses a very, very high dimensional model, like hundreds, thousands of dimensions, but it tends to pack all the data into small areas. So it clusters everything in small places in the dimension. So you will need to have high-dimensional metrics, but they are not complicated. Everything sort of becomes Euclidean, if you like. So nearest neighbors, that kind of calculation, or convex halves, those kind of things would work perfectly. So what I'm trying to say is that, yes, projection is not the right way to do it. It's practical just for the nice drawings. But still, you want to leverage relatively simple indicators because that's sort of the spirit of the very, very large dimensional space.
Thank you.
Okay, thank you very much.
Thank you.
Francois.